All right, the final type of inequality we're going to look at is rational inequalities. Before we do that, let's do a quick review of rationals. So when we look at rational functions, biggest thing to remember here is ratio. And when I think ratio, I think fraction. So our very first example we did of a linear was a fraction. However, the difference with rationals is it is a ratio of two polynomials. So there will be an x in the denominator. Okay, if there's ever an x in the denominator and it's a fraction, obviously there would have to be a fraction if there is a denominator, then it is a rational function. And there is some things you need to be aware of when we're looking at rational functions. We need to be aware of when something is continuous or its continuity. Okay, so the graphs of rational functions may have breaks in continuity. So that means you won't be able to trace the function without picking up your pencil. So some options of some breaks would be if I was driving along and there's a hole in my graph. Another option would be if there was like a vertical asymptote where you can't touch. It's that little invisible line. So here's a little example with the vertical asymptote. Breaks occur at values excluded from the domain, okay? So numbers that you can't plug into the function because you would get an error. So here's some examples. Here is a rational function. I know it's rational, there's an x in the bottom. Where would there be an error in the domain? It's whenever your denominator equals 0, because you can't divide by 0. So I have x plus 3 equals 0. So x equals -3. If I were to plug in -3, I would get 0 in my denominator, which is a domain error. So what is happening here is what we call a vertical asymptote at x equals -3. On our next function, where is the discontinuity here, to where our denominator is equal to 0 again. So there is a discontinuity when x equals 6. Once again, it's a vertical asymptote, a VA. The final example is a little bit different. If you go ahead and look at it, the numerator and the denominator can simplify. If that ever happens where it can simplify like that, that is where a hole occurs. This is an example of a hole where you're going along and then all of a sudden there's a value excluded from the function. So we have a hole in this case, and it's when x plus 4 equals 0. So at x equals -4 is a hole. That's a discontinuity. And then whatever's left in your denominator, that's your vertical asymptote. So we have a vertical asymptote when x minus 1 equals 0, so at x equals 1. Okay, so these are all of our discontinuities. So what causes discontinuities? There's actually 3 of them. You know 2. I just told you we got our vertical asymptote. We got our holes, vertical asymptotes. And then lastly, the other option is there's also horizontal asymptotes. So let's go ahead and look at these types of discontinuities. The first one is our vertical asymptote. It's a line that the graph of the function approaches but never touches due to a domain restriction. So we looked at this example. We have x minus 3 in our denominator. So since our denominator can't equal 0, x cannot equal 3. So that's why we have a vertical asymptote at x equals 3. Our function itself will never touch it. Then our point of discontinuity, it's also referred to as a hole. Holes occur when you have a value excluded from the domain but cancels out when the function is simplified. Those are really hard to see on your graphing calculator, but they exist. So if you were to graph it out, if you look at this one, x plus 2's, those cancel, so that means there's a hole there. So it means there's a hole when x equals -2. So if I go to -2, you'll see on my graph there is a hole. This one has no vertical asymptotes because the denominator, there's nothing left after we do that simplifying. And then a horizontal asymptote. That is a line of the graph that the graph of a function approaches but never touches horizontally. So if you go ahead and take a look here, right here is our horizontal asymptote. And it is at y, remember those lines are that, y equals 1. The way you can find that out from the function is you take the degree from the highest degree from the numerator and the highest degree from the denominator. So remember, degree is your variable with the highest exponent. So this is a degree 1, and then this is x to the first, so this is also degree 1. So you would take x over x, and this simplifies, those cancel to be just number 1. So my horizontal asymptote is at y equals 1. When we are looking at horizontal asymptotes or end behavior models, those are your horizontal, I'm just going to go HA. There's kind of 3 options that could happen. So if the numerator's degree is greater than the denominators, then infinite end behavior which occurs. So it's either positive or negative infinity. So here's a little example. If I have my function f of x equals x to the third plus x all over x to the just x. Let's just do x. All right, to find the end behavior, you take your biggest degree of each one, and we would simplify. So I have x to the third over x. Okay, remember when I have exponents, it's become x squared. So this one, my end behavior behaves like an x squared function. What this tells me is that there is no horizontal asymptote. Okay, so if it ever simplifies to another polynomial, that means there's no horizontal asymptote. If the denominator's degree is greater than the numerator's, then the end behavior approaches y equals 0. So let's just flip this around. If I have g of x, if I have x over x to the third, okay, I would have this simplified. This is x to the first, x to the third, so I'd have 1 over x squared. Okay, whenever I have a variable left in the denominator, and there's nothing in the numerator, there's always going to be an asymptote at y equals 0. Okay. And then the last one is actually your favorite one. It's kind of like the little example we went over, is if the degrees equal. So what if we have h of x equals 2x to the fourth over x plus 4x to the fourth. My biggest degree in the numerator, always take the coefficient in front as well, is 2x to the fourth. And then the bottom is 4x to the fourth. Those cancel. I'm left with 2 over 4, which reduces to 1/2. So my horizontal asymptote for that one is y equals 1/2. This is a lot to take in. Don't worry, we'll go over it again, but just kind of start seeing it and start recognizing where the horizontal asymptotes occur. In our next slide, we'll go ahead and go over an example.